The columns of the Parthenon stand with joints so tight that a blade of grass cannot slip between them. The precision is measured in fractions of a millimeter, achieved 2,500 years ago. And the architects who ordered those stones into place left behind not a single scaled drawing, no blueprint in any sense we would recognize. How did they build this without a single page of plans? The answer changes everything you thought you knew about ancient intelligence. Blueprints as we know them are a recent invention, dating only to the 18th century, a system of measured diagrams meant to control every detail before construction begins. So what did those ancient builders have instead? The first answer is almost disappointing. They used simple tools, plumb bobs to find true vertical, squares to check right angles, lengths of knotted string to measure distances, and a handful of geometric rules passed down so carefully that a master could recite them like a prayer. Those tools explain how a single wall or a row of columns could be made straight and plumb, but they do not explain how an entire temple or pyramid or cathedral was conceived, coordinated, and executed across years of work by hundreds of hands that never saw a single overhead plan. That requires something deeper, a kind of knowledge that did not live on paper but in the minds of the builders themselves, and the method for scaling that knowledge from a simple square to a mountain of stone is the real mystery. What systematic understanding allowed them to conceive and execute structures of such scale and accuracy? That is the puzzle we must unravel. Now consider the sheer scale of what we are asking. On a modern site, everyone reads from blueprints, digital models, a shared set of instructions. But imagine coordinating the placement of a 2-ton limestone block across a leveling plane that covers more than 13 acres, with no document telling you where it goes, no drawing showing how it fits with the next block, and no way to check except by eye and a piece of string. That is exactly what the builders of the Great Pyramid faced, and they did it so accurately that the base of the pyramid varies in level by less than an inch over an area large enough to hold several football fields. But it gets stranger. Many of these cultures had no written language at all. The Inca, the pre-Columbian builders of the Andes, left no known form of writing, yet their stone walls fit together with joints so tight you cannot slip a razor blade between them. So if there were no written plans and no written rules, how did the knowledge survive? A blueprint can be filed, copied, mailed. An unwritten rule must live in memory, in ritual, in the hands of the mason. This is design not by drawing but by rule, a rule that tells you the angle, the ratio, the repetition, all encoded in a system you carry in your head. But here is the complication. If the rule itself is unwritten, how do you make sure a mason in one generation carves the same curve as his grandfather? How do you maintain consistency across hundreds of workers and decades of time? But to see how one ancient culture solved this, we have to go back to the banks of the Nile, where the first great builders left us a clear clue. The clue on broken pottery comes from the Nile. It reveals an Egyptian system so consistent it left its signature across 3,000 years. At its heart was the royal cubit, the length of a pharaoh's forearm, roughly 52 centimeters, divided into 7 palms and 22 digits. The cubit was far more than a measuring stick. It was a design language. Every part of a structure could be expressed as whole numbers of cubits, palms, or digits. A builder could describe a complex building using nothing but numbers. They did not draw the whole thing to scale. Instead, we have small sketches on limestone flakes and broken pottery, known as ostraca. These show parts of a design, a column base, a doorway, a wall section, often drawn on a grid. The grid was a key invention. On tomb walls, artists used it to transfer proportions from small designs to full-scale masterpieces. That grid gave builders something more powerful, the ability to define a slope using the Seked, a simple ratio of horizontal run to vertical rise. For the Great Pyramid, the Seked was about 5.5 palms per cubit of rise. That single number, passed from architect to architect, ensured every course of stone followed the same angle with exacting precision. The Rind mathematical papyrus from around 1550 BC includes problems for finding a pyramid's slope, a granary's volume, and a circle's area. Yet no complete blueprint for any pyramid has ever been found. They built using models carved from stone or wood, small representations that showed the form but not the internal dimensions. From those models and generations of oral tradition, the knowledge was passed down. The Cubit, the Seked, and the grid were the design files, stored not in a drawer but in the hands of every master mason. This was not a limitation but a precision tool, elegant in its economy. The same Cubit that laid out a farmer's field could also lay out a pyramid. Because the system was codified in the body and in simple ratios, it worked across centuries and thousands of laborers without a single sheet of paper. The Egyptians had solved the problem of coordination and consistency by making the design rules so fundamental that every stone knew its place. These monuments were not guesswork. They were products of a rigorous, portable, remembered geometry. The Egyptian approach was practical and repeatable, built on a grid and a single ratio that governed every course of stone. But in Greece, architects aimed for something more. They wanted the building itself to feel right, not just stand up. They developed a system based on a sacred proportion that could make a temple look harmonious from every angle. The key was a module, often the diameter of a column at its base. Once that single measurement was chosen, every other dimension, the spacing between columns, the height of the entablature, the width of the steps, was determined by multiplying or dividing that module by simple ratios like 2:1 or 3:2. There were no drawings that scaled up the whole structure. Instead, the design was embedded in the proportional relationship itself. Builders memorized these rules and passed them down through generations of apprentices, carving sample details into stone for reference but never producing full plans. This system was so refined that it could account for the way our eyes trick us. Stand at the foot of the Parthenon and you notice something strange. The columns bulge slightly in the middle and the floor curves upward toward the center. That's not a mistake. It's a deliberate optical correction called entasis, designed to counteract the illusion of sagging that a perfectly straight line would create. The Greeks knew that a straight line seen from ground level bends in the mind, so they bent the stone the opposite way. That kind of adjustment required deep experience, not a calculation on paper. The architect had to know, from years of watching stone in daylight, exactly how much curve would make the temple look straight. Later, the Roman writer Vitruvius wrote down many of these principles, but the original Greek architects never needed a manual. They carried the ratios in their heads and passed them through the hands of masons who understood the language of proportion as instinctively as a musician understands harmony. It was a holistic system where every part referred to every other part, and the building itself was its own best blueprint. But the Greeks were far from the last to perfect this approach. The Romans took the idea of proportion and pushed it even further, using a new material that freed their forms from the limits of stone and made the blueprint itself an afterthought. The Romans took that tradition and did something unprecedented. They stopped carving buildings out of stone and started casting them. Their secret was concrete, a mix of lime, volcanic sand called pozzolana, and rubble. Pozzolana came from the region around Vesuvius, and it gave Roman concrete a remarkable property. It could set underwater and grow stronger over time. But concrete alone isn't a building. It needs a shape, and that shape came from wooden formwork, a temporary mold built on site. The formwork was the design. Once the carpenters had erected the wooden skeleton, the concrete was poured in and left to cure. When the mold was stripped away, the building stood complete. So the blueprint was never a sheet of parchment. It was the wooden box that held the liquid stone. The Parthenon in Rome is the ultimate example. Its dome spans 43 meters, the largest unreinforced concrete dome ever built. Inside, the coffers, the recessed panels that lighten the weight, are arranged in 5 rings that diminish in size as they climb. How did the Roman engineers plan that geometry without a drawing? They likely built full-scale templates on the ground, then adjusted them as the dome rose. The entire construction was a process of continuous decision-making, guided by the wooden mold itself. They didn't need to calculate every coffer on paper because the formwork provided the physical grid, and the oculus at the top, the open eye that lets in light. That was simply a gap left in the concrete, a negative space made by the mold. Few Roman architectural drawings survive. What we have suggests that builders used small-scale models and verbal instructions rather than comprehensive plans. The design was fluid, refined during construction. When the concrete cured, the building became its own record. The Romans proved that you could create the largest interior space in the ancient world without a single sheet of paper. The blueprint was the mold, the material, and the skilled hands that shaped them both, a 3-dimensional idea brought to life through making, not drawing. The Roman method was brilliant, but it belonged to a world of poured concrete and wooden molds. In medieval Europe, builders faced a different challenge. They had to raise vast cathedrals from cut stone, using nothing but geometry scratched into the ground. Imagine walking into a dark side chamber of Chartres Cathedral centuries ago and seeing the floor covered with faint lines and arcs. That was the tracing floor, a full-scale layout of the building's design, drawn with a chalk line and compass. The master mason didn't sketch a blueprint on parchment. He took a piece of chalk, a long string, and a pair of dividers, and he marked the geometry directly onto the stone pavement. This geometry was not arbitrary. It was built from sacred shapes, especially the vesica piscis, the almond-shaped intersection of 2 circles. That shape governed everything from the width of the nave to the height of the vault. The entire cathedral became a symphony of interlocking circles and squares, all derived from a single measured line. At Rheims, the tracing floor still exists, a palimpsest of chalk lines layered over centuries. You can see how the architect laid out the plan for the flying buttresses, the ribs of the vault, even the spacing of the columns, using only a compass and a straight edge. No numbers were needed, just proportion. The master masons carried this knowledge in their heads. They learned it as apprentices, repeating the same geometric constructions until they became second nature. Each generation added its own refinements, but the core method remained unchanged. You could build a cathedral from the ground up by knowing how to inscribe one shape inside another. The design was not on paper because paper was expensive and rare. It was in the hands and eyes of the men who swung the hammer. When you stand in the nave of a Gothic cathedral today, the spaces feel inevitable, as if they could not be otherwise. That is because they were generated by a logic that was older than writing, older than drawing. The medieval builder did not need a blueprint because the blueprint was implicit in the geometry he carried in his mind. He drew it on the floor, walked around it, corrected it by eye, and then built upward from those chalk lines. The tracing floor at Chartres is not just a tool. It is the ghost of a design process so direct that the plan and the building were one continuous act of making. The tracing floor was the visible record, but the hidden engine of medieval design was the mason's lodge itself. A physical building often adjacent to the cathedral, the lodge was where apprentices lived and worked for years. It was not just a workshop, it was a living library of architectural knowledge. Every master mason carried a mental catalogue of geometric formulas, but he also kept a set of full-size wooden templates, shaped and notched to match every arch, rib, and window tracery in the cathedral. These templates were the working blueprints cut from planks and stored on pegs. When a stone needed carving, the mason held the template against the raw block and traced its outline with a point. No drawing, no scaling down. One template could be used for dozens of identical stones, and when the design changed, the carpenter simply cut a new profile. The layout worker passed along geometry, but the templates preserved exact shapes across years and even decades of construction. The lodge also enforced a strict hierarchy. The master mason controlled the overall design, but he taught his journeymen through hands-on repetition. Each new recruit began by copying standard joints and moldings, learning the proportions by eye and touch. To protect their hard-won knowledge, masons developed a system of private marks and symbols carved into the stones themselves. These marks identified the individual carver, tracked payment, and sometimes conveyed assembly instructions. The written contracts we still have from the period deal almost exclusively with wages, material costs, and deadlines, never with the design itself. That knowledge stayed inside the lodge, passed from master to apprentice, and it would be lost if the lodge lost its living memory. When you consider the scale of a Gothic cathedral, hundreds of diverse stones, each cut to fit exactly once, the system was remarkably efficient. The blueprint was not a sheet of paper. It was a community of skilled hands, a rack of wooden templates, and a set of geometric rules etched into a floor that would be covered before the altar was even consecrated. The blueprint was a community, but what happens when a civilization builds without any writing at all? No contracts, no mason's marks, not even a symbolic system to record a single measurement. That was the reality for the Inca, and they produced some of the most astonishing stonework on earth. At Sacsayhuaman, the fortress overlooking Cusco, you'll find walls made of enormous polygonal stones. They fit together like a three-dimensional jigsaw puzzle, but the joints are so tight that you cannot slide a piece of paper between them. Geologists have gaped at the precision. Some stones have 12 or more faces, each angled differently, and every face matches its neighbor perfectly. And there's no mortar to fill the gaps, so how did they do it without plans, without templates, without writing? The evidence suggests a raw, iterative process. Workers selected boulders from nearby quarries. They pounded the stone surface with harder rocks, gradually shaping one face at a time. Then they lifted the stone into position, probably using log rollers and earth ramps, and test-fitted it. Where it didn't quite match, they lowered it and hammered away another few millimeters. Repeat, sometimes dozens of times, until the stone seated flush. It was trial and error on an industrial scale, and because no two stones were the same shape, every single block was a unique problem. The method had a hidden advantage. Those irregular, interlocking joints made the walls incredibly earthquake-resistant. When the ground shakes, the stones can shift slightly and settle back without collapsing. Modern engineers have studied Inca masonry and come away humbled. Yet the Inca had no written language to record any of this knowledge. No building codes, no diagrams, no instruction manuals. Everything a mason knew was learned by watching, by doing, by failing on the job. The system worked because the knowledge was stored not in a lodge of specialists, but in the hands of every builder. Here's the complication. If they had no writing, no templates, and every stone required custom fitting, how did they coordinate projects that moved thousands of tons of stone across the Andes? The answer may lie not in the stones themselves, but in something else they left behind, something the Maya on the other side of the continent also used as their blueprint. The Inca left something else behind, not paper, not templates, but a different kind of blueprint, the sky itself. And across the continent, the Maya had been reading that same blueprint for centuries. At Chichén Itzá, the Pyramid of El Castillo is famous for a very specific effect. Twice a year, at the spring and autumn equinoxes, a shadow in the shape of a serpent slithers down the side of the pyramid, connecting a carved serpent head at the base to a stone body. This wasn't an accident. To create that effect, the builders had to align the structure so precisely that the sun's angle at a specific time of year would cast exactly that shape. They had no blueprints, they had no protractors. What they had was time and observation. Generation after generation, priests and architects tracked the positions of the sun, the moon, and Venus using simple tools. A stick in the ground called a gnomon, and a length of string to measure the shadow's length and direction. They recorded these observations over decades. Then they translated the patterns into stone. The pyramid itself became a permanent calendar. Its 4 staircases have 91 steps each, plus the platform on top, giving 365 days. The 9 terraces correspond to the number of months in the Maya calendar. Every element was a statement about time, and it wasn't just this one building. The Caracol Observatory at Chichen Itza has windows aligned to the extreme positions of Venus. The Venus platform near El Castillo is aligned to the planet's rising points across its 8-year cycle. The Maya had a written astronomical record, the Dresden Codex, which tracks Venus with remarkable accuracy. But those tables were for prediction, not for architecture. The design of the buildings themselves came from sightlines and shadow lengths, tested and refined on the ground. Their blueprint was the movement of the heavens, embodied in stone. But not every ancient culture looked to the stars for their design rules. Some looked to a book. In China, around the turn of the 12th century, a government commissioner named Lai Jai compiled a manual that would become the most influential architectural code in East Asian history. The Yingzao Fashi, or Treatise on Architectural Methods, was published in 1103 during the Song dynasty. It was not a book of blueprints. It contained no plans for a specific building. Instead, it was a set of standardized rules, a recipe book for construction. At the heart of the manual was a modular system called Kai Fen. The building's proportions were derived from the dimensions of the timber itself. A single module, the Kai, was defined by the size of a standard structural beam. Everything else, the height of columns, the depth of roof overhangs, the intricate bracket sets called dugong that support the eaves, followed from that one module. The manual specified 8 grades of timber, each suited to a different scale of building, from a small hall to a great palace. The Yingzao Fashi gave detailed dimensions and proportional relationships, but it did not dictate the final layout. The master carpenter was expected to adapt the rules to the site, the materials, and the occasion. The manual was a tool for consistency, not a straitjacket. It ensured that a government building in Kaifeng would follow the same structural logic as one in Hangzhou, but local adjustments were assumed. Compare this to the Greek modular approach we saw earlier, where the column diameter set the proportions. The Chinese system was far more rigidly codified, written down and enforced by the imperial bureaucracy, yet it still required a living architect to interpret the rules. So here we have a culture that used writing to transmit architectural knowledge, but the result was not a modern blueprint. The Yingzao Fashi was a code of practice, a memory aid for a tradition that had been passed down orally for centuries before it was recorded. The design of a building still existed in the mind of the master. The manual only provided the grammar, not the sentence. But nowhere was architecture more tied to a cosmic blueprint than in Cambodia, where the entire city of Angkor was built as a reflection of the Hindu cosmos. But nowhere was architecture more tied to a cosmic blueprint than in Cambodia, where the entire city of Angkor was built as a reflection of the Hindu cosmos. The centerpiece, Angkor Wat, was not just a temple. It was a physical representation of Mount Meru, the mythical home of the gods, surrounded by a moat symbolizing the cosmic ocean. To build such a structure without architectural drawings seems almost impossible, Yet the Khmer architects achieved it through a deep integration of cosmology, astronomy, and geometry. The temple's layout follows a precise axial grid aligned to the cardinal directions, with the central tower rising almost 60 meters above the ground. That tower represents the peak of Mount Meru, and the surrounding galleries symbolize the mountain ranges that encircle it, but the design went further. The entire temple was oriented so that on the summer solstice, the sun rises directly above its western entrance, casting light along the main axis. This alignment was not accidental. It was calculated using simple observations of the sun's path, likely with a gnomon and a chord. The proportions of the temple, the width of the causeways, the height of the towers, the spacing of the galleries, followed a repeating unit known as the hat, roughly 43 centimeters, but no one has found a plan on paper. No Khmer architectural drawing survives. Instead, the design was encoded in ritual knowledge, passed down through generations of priest architects who memorized the ratios and alignments. The entire city of Angkor was a vast cosmological grid, with temples positioned to mirror the stars and the cycles of the moon. What we see at Angkor Wat is a blueprint that existed only in the mind, a mental model so thoroughly internalized that it could be realized in stone without a single sketch. The cosmos itself was the plan, but all these cultures shared something. They did not get it right the first time. The secret to their success might be that they built, rebuilt, and adjusted, a process that blueprints can sometimes stifle. And that's exactly what all these cultures had in common. They built, they watched, and they adjusted. We often assume that without a fixed plan, ancient builders were improvising blindly. But the truth is the opposite. The absence of blueprints gave them something modern construction rarely enjoys: the freedom to learn as they built. Consider the great medieval cathedrals. The vaults of Beauvais Cathedral collapsed in 1284, just a few years after they were completed. That could have been a catastrophic failure, but it became a lesson. The builders didn't start from scratch. They reinforced the piers, changed the proportions of the upper walls, and tried again. Today the cathedral stands, incomplete but structurally sound, a monument to iterative design. A modern architect with a sealed blueprint would have needed months of revisions and legal approvals. The medieval master mason simply walked over, looked at what went wrong, and told his team to do it differently. The Parthenon offers another glimpse. The subtle curvature of its platform and columns, known as entasis, is usually described as an optical correction. But recent analysis suggests it was refined during construction. The builders started with a slight curve, saw how it looked in the morning light, and made it more pronounced. They didn't just trust a paper calculation, they trusted their eyes. Medieval masons even built symmetrically paired towers in stages, leaving one slightly taller as they watched how the stone settled. They learned from gravity itself. This constant feedback loop produced structures that were both resilient and elegant. In contrast, a modern blueprint fixes every dimension before the first shovel hits the ground. If a flaw emerges, changing it means tearing up the plan, delaying the schedule, and fighting the budget. Ancient builders could adjust on the spot, because the design was never locked in stone until the last block was laid. What we see as a limitation was actually their greatest strength. They weren't hindered by the lack of blueprints. They were liberated from them. Each project became a living conversation between intention and reality. And that conversation demanded an intimate knowledge of materials, a knowledge that could never be written down on paper. That constant feedback loop shaped more than just the building's form. It demanded an almost tactile intimacy with the materials themselves. Roman concrete is a perfect example. Modern engineers have discovered that the ancient blend, using volcanic ash from Pozzuoli, actually self-heals over time. Tiny cracks fill with calcium deposits as water seeps through. The builders could never have predicted that with a formula on paper. They learned it by watching pavements and harbor walls survive for decades. then passed the recipe down as a craft, not a chemical equation. The Inca took a different path. At Sacsayhuaman, the massive polygonal stones shift independently during earthquakes, settling back into place because the joints are cut with a slight taper. Modern replicas made with precise blueprints often crack under the same stress. The Inca didn't calculate seismic loads. They felt them. They carved, lifted, and adjusted until the stone told them it was right. Medieval cathedral builders understood load paths through flying buttresses without any statics textbook. They knew that the thrust from a vaulted ceiling would push outward, and they thickened the buttresses only where experience told them it was necessary. When a buttress failed, they rebuilt it with a slightly different slope. The knowledge that worked was the knowledge that survived. This was not theory. It was a living encyclopedia written in calloused hands and seasoned intuition. Every generation refined it, but they never abstracted it onto paper. The blueprint didn't exist as a document because the blueprint was inside the builder's body, and that kind of wisdom required something else entirely. That wisdom required an extraordinary mental architecture. Master masons could walk across an empty field, scratch a few arcs in the dirt, and see in their minds a cathedral 200 feet high. Research on modern experts with high visuospatial ability shows the brain can rotate complex forms, test fits, and predict load paths without any external model. Ancient builders pushed that skill to its limit. They used small clay mock-ups to experiment with vault shapes, then scaled the proportions in their heads. Oral traditions carried detailed dimensions not as written numbers but as recitations that described every chamber and passage. The architect's mind became a living structure, a memory palace where each room was a mental image of the real stone to come. Every curve, joint, and load path existed first as a precise mental image, tested and adjusted before any stone was cut. This mental architecture was refined over centuries, passed from master to apprentice through direct experience. Today we have largely outsourced that cognitive muscle to paper and software. So after thousands of years of building without blueprints, the question remains: what did the invention of blueprints actually change, and did we really gain more than we lost? So what did the invention of blueprints actually change? On one level, the answer is obvious. Blueprints made it possible to build faster, to coordinate vast teams across continents, and to reproduce a design exactly anywhere in the world. That efficiency is not trivial. It gave us skyscrapers, airports, and every modern city grid. But the trade-off was real, and it became visible the moment a construction site had to adapt. A blueprint is a fixed plan. If the soil behaves differently, if a rock turns out to be softer than expected, the builder has to stop, call the architect, issue a change order. What was meant to eliminate uncertainty instead created a new kind of rigid dependency. Ancient builders never had that problem. Their design lived in their hands and eyes, and every stone they laid taught them something they could use on the next one. That flexibility is not just a historical curiosity. Engineers today are studying Inca stonework to learn how buildings can survive earthquakes without rigid joints. Roman concrete compounds are being analyzed for their self-healing properties, properties that arose not from a formula on paper, but from generations of mixing, testing, and adjusting. And some of the longest-standing structures on the planet, the Parthenon, the Great Pyramid, the cathedrals of Europe, were built by people who never drew a single floor plan at scale. They outlasted countless modern buildings because their builders understood the materials and the loads through direct experience, not through a symbol on a page. This is not to say we should throw away blueprints. That would be absurd. The point is that a blueprint is a tool, not a substitute for understanding. The ancient architects didn't lack design. They had a different kind of design, one that was embodied, iterative, and deeply connected to the place and the material. When we outsource that intelligence to paper, We gained reproducibility and speed, but we also lost something. A way of knowing that forced every builder to think like an architect and every architect to think like a builder. The legacy of those ancient methods is not that we should go back to drawing arcs in the dirt. It is that the most powerful tool on any project is still the human mind, trained by experience and willing to adapt. That lesson has not changed. What has changed is how often we choose to remember it. So the next time you walk past an old stone wall or stand beneath a towering cathedral, consider the knowledge locked in every line. Egyptian grids, Roman concrete, Inca stone fitting, Chinese manuals, each one a distinct method. Which one would you trust to build your own home? Let me know in the comments. Subscribe to uncover more hidden genius from ancient civilizations, the stories textbooks leave out. Their blueprint was the world itself. Read through geometry, memory, and generations of trial.